James Balog has a near-fatal attraction to ice.
Oh, God, that is intense.
His fascination is leading him farther and deeper into the cryosphere, the frozen regions of the Earth.
I feel like I'm not on planet Earth right now, like I'm in truly some extraterrestrial environment. The world isn't supposed to look like this.
What began as a photographic assignment has become a mind-blowing odyssey into an unpredictable world, where entire landscapes teeter between solid and liquid states. On the Greenland ice sheet, a crack opens, and a mile-wide lake pours down a 3,000-foot chasm.
But this water is just drilling down into the ice sheet.
One of the world's biggest glaciers shears off an iceberg that is nearly 1,000 feet thick.
You're not supposed to be able to witness things like this. Human beings don't generally get to see these massive features of the landscape changing and vanishing in front of your eyes.
Changes in the ice are normal. It is volatile and constantly in flux. But what Balog is witnessing suggests something extraordinary is going on. His passion is to document it and help scientists understand these monumental changes.
Many of the changes we're seeing are unfolding faster than our ability to really understand them.
Our relationship with ice is one that has very dramatically, if not violently, shifted from one of, don't worry about it, to one of, boy, you know, this is one of the most important controllers of the future environment of the planet.
Balog's work frames one of the most important scientific questions humans have ever faced. How fast will the world's glaciers and ice sheets melt? And what will all that melting mean for us? As scientists try to figure it out, Balog is finding evidence to help answer some of these questions.
Got it.
His Extreme Ice Survey is the largest photographic study of the cryosphere ever attempted. He is deploying 26 time-lapse cameras on glaciers across the northern hemisphere and programming them to shoot a frame every daylight hour for 3 years. It is a massive challenge in some of the most hostile regions on Earth.
So everything we're trying is getting thwarted. I'm trying not to be frustrated.
But the pain is starting to pay off, with thousands of frames revealing unparalleled changes in the ice.
My hope is that it will be powerful and immediate enough that people will say, yeah, I get it, I understand it. Okay, this is real. This is forensic evidence of the reality of what's happening.
The fact that the ice is changing is nothing new. Over the millennia, the expansion and contraction of ice across the continents has fundamentally altered the planet, gouging out lakes and valleys and pushing man around the Earth.
The waxing and waning of the ice sheets have been implicated in who lives where and what they do, and there are even some people have suggested that we're humans now, in part because we were responding to the changes in our environment that were linked to the growth and shrinkage of the ice.
In the past, the cycle of ice ages and periods of warming were caused mainly by shifts in the Earth's orbit around the Sun. But now, humans seem to be driving these changes. Since the Industrial Revolution, our burning of fossil fuels has ratcheted up the output of greenhouse gases, like carbon dioxide, which trap heat in the atmosphere. Temperatures are climbing, and the ice is melting faster than ever.
I think that if we stay on the path we're on, we will change the amount of land ice, and therefore we will change sea level. The real questions, the more complicated ones, are how fast are we going to get there? How much is it going to rise? Can we put the brakes on it at any point?
It is the speed of the melt that is most astonishing. And nowhere is it happening faster than in the glaciers along the west coast of Alaska. Glaciers are like massive ice factories. High in the mountains, snowfall builds up and is compacted over hundreds of years. Gravity pulls it down in colossal rivers of ice. Some glaciers flow all the way to the ocean, shearing off icebergs in a process called calving. Over the last 40 years, temperatures here in Alaska have risen about 4 degrees Fahrenheit, twice as fast as the global average. Now, these rivers of ice are flowing faster and crashing even more spectacularly into the sea. Some people are taking advantage of the glacial fireworks while they last. Surfers towed in by jet skis are playing a dangerous game of chicken with the ice. It is rapidly calving glaciers like these that are the main contributors to rising sea levels. Alaska's Columbia is one of the biggest ocean-feeding glaciers in North America. In the early 1980s, the Columbia started flowing faster and began calving far more ice into the ocean than was being replenished by snowfall upstream. Baylog and the Extreme Ice Survey glaciologists are trying to figure out how much ice the Columbia is losing and whether or not it can survive. In the shallow waters of Columbia Bay, melting icebergs jam up before being carried away with the tide. This is the end of the line for the Columbia, a crystal maze of deteriorating ice that draws Baylog in.
Out here. Basically, we're looking at a whole landscape full of crystals. It's a cool spot. There's a lot of power here. It seems to be calm, it seems to be still, but there's this constant energy of the sea coming and going and carrying this huge glacier away. Every time you go in here, you're taking a risk because these bergs are inherently unstable. But you get seduced by the beauty of it. You know, you just get drawn in. It's like the sirens of Columbia Bay pulling you in, luring you in, going, come to me, come to me, come to me. And you just keep following these beautiful objects back through the labyrinth. Okay, Jeff, right about on this line here. The light that really makes these sculptures come alive is bouncing off the surface of the water. So the bergs are lit from within. Oh.
At the Extreme Ice Survey camp, glaciologist Tad Pfeffer tracks the flow of the Columbia. As the glacier moves, it churns up dirt and rocks that collect on its surface. The Columbia is so vast, it's hard to imagine it vanishing. Pfeffer and his colleague Shad O'Neill are taking its vital signs, measuring the speed of the glacier over several years to determine whether it's speeding up or slowing down. To do this, they fire a laser survey gun at reflective targets that they must deploy on the surface of the ice. As the pilot hovers a few inches above the glacier, O'Neill positions the target onto the ice. Pfeffer locks on to the target and shoots a laser that reflects back to the stationary gun, recording the position.
I got it, you're good. Come on back. Okay, first one down. 1.1 kilometers away.
The target moves with the ice. By tracking its movement with a laser over several days, they will be able to calculate the speed of the Columbia. Just down the fjord, Balog and Extreme Ice Survey engineer Adam LeWinter climbed down to one of the time-lapse cameras they installed a year ago.
Oh, yes, here it is.
Still all there?
Yeah, the camera's here, but what happened to the glacier? When I was here a year ago, the calving face was just right there. All right, we have pictures.
The time-lapse brings to life the dynamic nature of the glacier, the ebb and flow of the ice as it calves.
It's a revelation. Every time we open up these boxes and download these images and bring them up on the computer and play them back, your eyes are popping out of your head.
Although calving is normal, the Columbia is hemorrhaging ice so quickly that in the last 30 years, the glacier has receded 10 miles up the fjord. Balog's time-lapse images capture a rate of retreat that shows no sign of stopping. In the last year alone, the Columbia lost another half-mile of ice.
I really never expected that we were going to see changes of anything like this kind of magnitude in the period of time we had to work on this.
This rapid calving of the Columbia is a symptom of its decline, but it's poorly understood. If Pfeffer and O'Neill can figure out what's causing it to calve more ice, it may help them predict the glacier's future. They're taking a curious tack by using earthquake technology to crack open the mystery of the ice. They're installing seismometers that pick up the vibrations of ice quakes, tremors that reverberate through the ice as it calves. From the seismic data, a pattern emerges that points to one clear culprit: water. They knew water was melting the ice, but it appears that it's prying the ice apart like a powerful lever.
You can hear meltwater running right now, and it's all getting stuck in the glacier. And if you have a fracture with high pressure water in it, it can ratchet the crack open.
The seismic record confirms that the calving events have the unique signatures of fractures caused by water. As rising temperatures create more surface melt, the water pours into the cracks in the glacier and wedges it apart. The result is increased calving and a quicker demise of the glacier.
Oh, there's a big one coming up from underneath. There it is.
Balog is seeing this powerful fracturing effect firsthand as the fjord below comes alive.
That basal ice has come up from the very bottom of the glacier, that dark blue out there. As the ice and the snow are squeezed together, the air gets driven out of it. And so the color becomes more and more pure. The air bubbles are what make it white. And so when the base of the glacier breaks up, you get these fantastic sapphires and turquoises boiling up out of nowhere, and that's what these bergs are.
Meanwhile, after several days of laser tracking, Tad Pfeffer knows how fast the Columbia is moving. 50 feet per day, 8 times faster than it was 30 years ago.
Go back to 1980. Here on this bedrock, we had ice above us 1,500 feet. Look at the trim line over there. That's where the ice surface was in 1980. And all of that volume is lost because this calving is so fast and snowfall upstream isn't resupplying it. So in that sense, yeah, it's going too fast and the glacier is kind of collapsing.
Pfeffer suspects that the Columbia is long past its tipping point, and it's only a matter of time before it withers away entirely.
This kind of ice is called dead ice. It's no longer part of the living active glacier. It's stranded up on the side of the ice stream, and it's melting away and collapsing. And as it does that, all the erosional debris that's on the top continues to concentrate until you have this ice covered in blackness.
I'm really interested in the mortality of the glacier right here. There's something very rich and very intense about the changing landscape. You know, I feel the end. I feel the death right here.
The problem is, it's not just the Columbia that's on its way out. Glaciers everywhere, across the Rockies, Andes, Alps, and Himalayas, are in their death throes.
The people that live near the mountains and watch the glaciers know that the world is changing. We are heading towards Glacier National Park without any glaciers. We're seeing, huge changes in Glacier Bay in Alaska and other places. If you go, if you look, you see it.
The consensus is that in the next 50 to 100 years, mountain glaciers almost everywhere will simply disappear. From the loss of mountain glaciers alone, sea levels will rise by almost a foot, displacing millions of people around the world. But the biggest cost will be the loss of these huge natural reservoirs of fresh water, water that 1/6 of the world's population depends on. The hardest hit will be in Asia, where nearly 1 billion people get their drinking water from Himalayan glaciers. The abrupt collapse of the world's mountain glaciers raises even more disturbing questions about the Earth's biggest tracts of ice: the polar ice sheets of Antarctica and Greenland.
The real wild cards are what the big ice sheets are going to do. We're already seeing the Greenland ice sheet start to behave in rather disturbing ways.
We're playing with fire, if you will, when it comes to the ice sheets. We don't know whether if we get these big, massive, freight train-like beasts going, whether we can stop them.
The potential for the polar ice sheets to flood the planet is staggering. If all of Greenland and Antarctica were to melt, the oceans would rise 200 feet. But over geologic time, these ancient bulwarks of ice have withstood many bouts with climate warming. Until a few years ago, scientists thought the ice sheets were simply too big and too dense to be an immediate risk. But the latest evidence is making them rethink. The first wake-up call came from the West Antarctic Peninsula. In the summer of 2002, a NASA satellite photographed a Rhode Island-sized slab of ice called Larsen B as it sheared off the ice shelf. Other collapses followed, turning the assumption that it would take thousands of years for the big ice sheets to melt on its head.
The ice sheets surprised us. We sort of thought that the little glaciers would melt when it got warmer and that the big ice sheets wouldn't do much. And all of a sudden, the big ice sheets started rumbling faster and the Larsen B was falling apart. And we said, whoa, that wasn't supposed to happen.
On the other side of the globe, Greenland's cache of ice is also showing signs that it's starting to feel the heat. In the last decade, temperatures here have shot up by about 5 degrees Fahrenheit. NASA satellites are already detecting a meltdown around the edges of the ice sheet. Global warming is hitting hardest in the Arctic, and all eyes are now fixed on Greenland's ice. Its next move could be the game changer for rising sea levels. In the heart of Greenland, Beilage scientists encounter an entirely different realm. A single slab of ice about 1,500 miles long and 500 miles wide. It's mid-July, and the summer melt on the Greenland ice sheet is in full swing.
It's sort of like an ice version of Kansas out here. It feels like you're out in the Great Plains, and it just happens to be white, and there's this vast dome in the sky overhead. It's unbelievable. There's no sound at all. No sound, except the wind and the water. It looks quite featureless when you just look horizontally, but as you walk over it and you look down on it, there's a tremendous amount of texture and detail on here. This entire surface is like one gigantic Swiss cheese.
During the melt season, the sun's heat transforms the surface of the ice, creating a landscape that constantly shifts between solid, liquid, and vapor. The meltwater courses through the ice sheet, searching for a path down. Figuring out how this complex plumbing works is essential for predicting the future of the ice sheet.
Oh, man. Look at that.
Whoa, that is intense. Oh my God. I can see, I think, maybe 250 feet down into the dark. No sign of the bottom. But this water is just drilling down into the ice sheet. There's this great unknown here. This great mystery of where does all this water go? And what does it do to the flowing and the melting of the ice sheeting, sending it out to sea? Nobody really knows.
Baylog wants to get a shot that delves deep into the underbelly of the ice. The only way to secure his ropes is to thread them through the ice sheet.
You know, this ice sheet is cooking down, melting a lot, so this whole top foot and a half where you would normally put an ice screw is rotten and loose. Whereas here we're actually using the ice sheet itself and the strength of the ice to anchor the ropes. So here we go.
All right, a little slack.
Okay.
Wow.
Yay. How about that?
These giant holes, called moulins, are thought to bore thousands of feet through the ice to the bedrock. But nobody has ever been down there to find out.
Oh, God. That's the first time I've really seen the hole down there. Dave, this whole balcony could go any second. There it goes. It's a strange, evil, gorgeous, horrible, fantastic place. Wow, I mean, there's hundreds of years of ice here layered in, and we're looking into the cross section of this life history of the glacier. And it's so beautiful, this insane aquamarine and all this scalloping and fluting from the water. What a spot.
Baylog is just scratching below the surface of the ice sheet. Below him is another half-mile of solid ice. In these compressed layers of the ice sheet, there are clues to how fast Greenland could melt. At the National Ice Core Lab in Lakewood, Colorado, a giant freezer stores over 45,000 feet of ice, drilled from 34 sites around the cryosphere. Dating back hundreds of thousands of years, these ice cores are time capsules that allow scientists like Jim White to peer deep into the history of ice.
This piece of ice is interesting because it has a couple of things you can see right away. One is there are bubbles throughout here. These bubbles are little packets of air. It's these bubbles we can take out and measure CO2 and methane and nitrous oxide. It's the only medium that really collects the atmosphere itself. The other thing you can see in here quite clearly is you can see the layers. And the thickness is going to tell you how much snow fell that year. So you get a couple of pieces of climate information and a dating scale just out of visually looking at this ice core.
Most importantly, scientists have identified a direct historical link between increases in greenhouse gases like carbon dioxide and steep rises in global temperatures. At every peak, big rises in sea level followed as Greenland's ice sheet shrank. The ice core records also reveal a particularly telling moment in Greenland's history. Roughly 125,000 years ago, temperatures rose by about 7 degrees Fahrenheit. The entire southern portion of the ice sheet melted, and global sea levels rose by over 10 feet. It was caused by a change in the Earth's orbit around the Sun, which increased temperatures and released carbon dioxide from the oceans. The more recent ice core record shows the potential for a similar meltdown. Right now, greenhouse gas levels in the atmosphere are even higher than they were 125,000 years ago, higher than they've ever been in the last 500,000 years. Temperatures are already following suit. The only explanation is the burning of fossil fuels.
What we see in this ice core is very solid evidence that what's happening today in the atmosphere is different. It's not a normal part of the climate cycle. It's something caused by human beings.
Rising temperatures are once again pushing Greenland towards a major meltdown. But what the ice cores can't tell us is how long it will take. The last time Greenland lost a significant portion of its ice, White suspects it happened over thousands of years. But this time, it could happen much faster.
And here we are now, fiddling with the dials of the climate machine, not quite knowing what's going to happen. And we know from these past records that the climate system can come up and bite us hard.
So far, global warming is biting hardest at the fringes of Greenland's ice sheet. Ringing the island are hundreds of outlet glaciers that act like pipes, draining the interior ice sheet out to sea through narrow fjords. In the late 1990s, many of these spigots began gushing more ice. One of the largest, Jakobshavn, is now pumping out over 40 billion tons of icebergs each year, more than any other glacier in the northern hemisphere. These icebergs reach the open ocean at Disco Bay. In this deceptively peaceful icescape, James Baylog is on the hunt for giant bergs. Some of these blocks of ice rise over 300 feet above the waterline, but 90% of their mass is hidden below.
Oh my God, these things are gigantic. If they roll over, we'll be swimming with the fishes. But right in here, there's this line of jewels as you come around the arc of this berg, and all the water drops are coming in, and the sun makes this fantastic necklace of jewelry along the edge of this. Oh man, let's do it again. There's something in there. It's making me crazy, actually, because there's a picture in here. There's definitely a picture in here. Wow, that was amazing.
"35 miles up the fjord from Disco Bay, Baylog's time-lapse cameras are stationed above the calving face to capture Jakobshavn's every move. Baylog has teamed up with glaciologist Jason Box, who has been keeping a close watch on Jakobshavn and other glaciers along the coast for the past 14 years.
The Jakobshavn Glacier is the king of glaciers in Greenland. It produces by far more icebergs and more ice flow than any other single glacier. This is really where the rubber hits the road in terms of sea level rise. Glaciers are, of course, very dynamic systems, but you don't really see that when you sit there and stare at them. We're able to observe with the time-lapse cameras at a much higher frequency, like every hour, whereas from satellite you can only observe the glacier every 10 days or so.
What they are finding is that the ice is far more sensitive to temperature changes than they thought. During the summer melt season, Jakobshavn is now moving at a clip of 130 feet per day, almost twice as fast as a decade ago. The faster it goes, the more pressure builds up behind the glacier's 400-foot-high calving face. This triggers more frequent and explosive calving events. In the spring of 2008, Beilag's team was staking out Jakobshavn and got lucky, capturing the largest calving event ever filmed. In the space of about an hour, a section of ice as wide as Manhattan sheared off the glacier.
We've underestimated the sensitivity of these systems. We are approaching the threshold of viability for the Greenland ice sheet, and that's when the melting occurs high enough on the ice sheet that no matter how much snow accumulates, there's net loss every year.
Greenland is already losing 150 billion tons more ice every year than it gains in snowfall. As temperatures go up in the coming decades, even more ice will be lost. The hard part is figuring out how much and how fast.
There's big questions now that we didn't think we were going to have to solve. They're hard questions. Ultimately, you crank up the temperature in the air and the ice sheet notices and it flows faster and it raises sea level. But how fast and how much are questions that really we don't have answers to.
Some of those answers may be hidden deep under the ice. The summer melt season on the Greenland ice sheet has grown hotter and is now 2 weeks longer than it was only a decade ago. Rivers of meltwater cut deep into the ice, creating a serpentine canyon that winds for miles.
This is one of the most exceptional landscapes I've ever seen in my life. You know, this looks so much like those incredible canyons out in the sandstone country in Utah. And you have that, except it's sculpted out of ice. It's like this huge, incredible cake sculpted by this river in here, and it's like the world isn't supposed to look like this.
As the summers heat up, features like this ice canyon are becoming more pronounced. But for all its beauty, it raises perplexing questions about the effect this water is having underneath the skin of the ice sheet. The strangest phenomenon is the mystery of the meltwater lakes. As the ice sheet cooks down, the meltwater collects in depressions in the ice, forming thousands of lakes, some over several miles wide and nearly 50 feet deep. From satellite images, scientists noticed that in midsummer, many of these lakes vanished overnight, leaving bright circles where the water once stood. Until recently, it was assumed that the water was absorbed and refrozen into the ice sheet. But Ian Jochen and Sarah Das have a hunch that the water could be having a deeper impact. These events are so unpredictable, nobody has ever observed them. But Das and Jochen just came close. A few days ago, a big lake by their camp suddenly drained out.
We were in the fog, so we couldn't see the whole lake. While standing right on the shore of the water, we started to hear some really loud booms and pops. And it was just extremely spooky. Cracks would run across the ground beneath your feet. It was all around you. It was a strange experience.
Frightening, but also fortuitous. They had placed a device that measures water pressure called a pressure logger in the bottom of the lake, hoping it might drain. If they can find the logger, their bet might pay off.
The fish line that we're following, it's tied at one end to our stations, and it's tied at the other end to an old plastic bottle that has a pressure logger attached to it, and that's sitting in the lake basin. And so we're following the line out, hoping that at the end we'll find it tied off to our loggers.
The loggers should reveal exactly when and how fast the lake drained. Everywhere, truck-sized blocks of ice litter the lake bed, evidence of the violent forces uncorked as the water rushed out.
I see
Hey,
it!
there it
Look
is.
at that.
Whoa.
In there, under the ice.
Watch your fingers. I'm on
There's one of them.
With the loggers in hand, they can now plot out the minute-by-minute account of the mass draining of the lake.
So what you see here on the left is early June when there's no water in the lake. And as more water fills the lake, the pressure goes up, the height of the water column goes up and up, up, continue to fill until about this point. And then on July 10th, boom, you see the lake drop in a matter of about 40 minutes.
GPS data reveals that so much water drained out so quickly, the surrounding ice was pushed up by several feet.
Well, as you can see from the blocks all around us, there's a tremendously violent event. You have a lake that's 2 miles wide, 40 feet deep, and all of a sudden it drops 3,000 feet through the ice. It would have basically been one of the tallest waterfalls in the world. The flow into these cracks in the lake bed is greater than the flow over Niagara Falls.
Instead of being absorbed and refrozen into the surface ice, they discovered that the water dropped all the way to the bedrock. There, it lifts and lubricates the ice sheet and accelerates its slide.
And if you have increased warming, especially in the summertime, over the ice sheet, you're going to just increase the supply of meltwater to the bed. And potentially that could escalate the speed up.
Their breakthrough solves the mystery of the meltwater lakes. They'd measured it, but because of the fog, they hadn't seen it happen. By sheer chance, the very next morning, Balog and the scientists would witness it firsthand. About a mile away from his camp, a smaller lake that was full only hours before suddenly starts to drain. Balog heads for the water line to try to find where the water is going.
This is the world's most treacherous footing. These wave cups are hard walking as it is, and with them just emerged out of the lake, they're slick as can be. There's so much water packed in there. It's just like grease on top of glass. Oh my God. Not being roped up here is one of the scariest, dumbest things I've done in my life. Where I'm laying right now was underwater just 6 hours ago. You know, there was a lake here, and the water depth of the lake was roughly 20 feet right here. And all of that that was overhead 6 hours ago is drained out and poured down this hole. And I can see maybe 250, 300 feet down there. I'm not feeling real comfortable out here.
This is really the first time that we've been able to observe these things firsthand actually happening. And it's really nice to see that our theories that we've pulled together from our instrumental records match our observations on the ground very nicely.
Now they know. These billions of gallons of water are finding a route under the ice and out to sea, lubricating the outlet glaciers and making them speed up. Das and Jacquin calculate that this lubrication effect accounts for about 10% of the increase in speed. So there must be another powerful force behind the surge of ice from Greenland. The latest ocean research may have found it. Around 1997, there was an abrupt 3-degree Fahrenheit jump in coastal water temperatures, exactly when the outlet glaciers began to speed up. At the foot of Jakobshavn Glacier in Disko Bay, Ian Howitt is investigating how the warming ocean could be eating away at the edges of the ice sheet.
Trying to get a handle on how the ocean and the ice interact. And so by that I mean how heat is transferred from the ocean, which is this huge source of heat, up against this ice sheet.
To figure it out, Howitt is using a capsule packed with sensors that record temperature, salinity, and depth at intervals going down 1,000 feet to the ocean bed. The measurements give Howitt an immediate picture of how the meltwater streaming off the glacier and the denser salt water below stack up like a layer cake.
So this plot is showing the increase in temperature with depth. What we see here is very cold, nearly freezing water at the surface, and then as we go down, it increases its temperature as it mixes with the warmer ocean water below. So this transition zone, this almost flat line, shows us that there's a very sharp transition between that fresh water and the salty ocean water below.
Howitt thinks the rush of cold meltwater coming off the glacier might be creating a vacuum at the calving face that pulls the warm ocean water underneath it, delivering heat directly to the base of the glacier.
One hypothesis is that as you increase the melt and you increase the force of this conveyor belt of fresh water going out of the fjord, you're bringing more heat from the ocean into the fjord to melt more ice, and that would be a strong feedback that could actually lead to more glacier melting. It's a much more dynamic environment than we've thought in the past.
The story of the mountain glaciers and the ice sheets shows that abrupt changes in the ice aren't the exception. They're the rule.
There are concerns that we get to some point beyond which strong feedbacks in the climate system kick in and cause changes that we're really unprepared to deal with.
The ice may have more surprises to come, but based on the latest research, the best guess for future sea level rise comes down to a simple calculation. In the next 100 years, the oceans will expand on their own as they warm, accounting for about a foot of sea level rise. Another foot will likely come from the loss of the world's mountain glaciers as they melt away. The ice sheets of Greenland and Antarctica won't disappear, but their combined melt is expected to add about another foot. The total equals an estimated sea level rise approaching 3 feet or 1 meter by about 2100. It may not sound like much, but over 100 million people live within 3 feet of sea level. Cities around the world will spend trillions building up coastal defenses. Low-lying regions such as Florida, Vietnam, and Bangladesh will be devastated. Many island nations will cease to exist. The consequences will test our ability to adapt like never before. But it doesn't stop there.
If we look beyond 100 years, the biggest questions might even be what we do. There's huge things we don't know about the ice sheets, but our uncertainty about what we decide to do may be bigger than that. But if we make it really warm, I think a whole lot of us get really nervous about what the ice will do.
This is going to be one of the pivotal moments in human history. Ice is too important for us in terms of the climate of the planet, in terms of sea level, in terms of the fundamental operating systems of the planet, for us to continue to ignore it.
The final chapter of Beilag's story plays out on the southern coast of Iceland, where he discovers an unrivaled confrontation between the ice and the sea. "8,000 years ago, the island was encased in ice, but now the last remnant of its ice cap is quickly disappearing. As the ice seeps down towards the sea, it discharges into a meltwater lagoon. Each day, the tide draws the icebergs out into the North Atlantic.
I'm not aware of any other place in the world where you can see this dynamic between the ice and the surf
in the same way. What I see in this ice is a unique sculpture by nature. Each one is a Hope diamond, you know, some really perfect, pure manifestation of form and color and texture. They come up here on the waves, they sit here for 12 hours after the tide goes out, then the tide comes back in, takes them away, and they're gone for good. And in that transitoriness, I see extinction. Our brains are programmed to think that geology is something that happened a long time ago or will happen a long time in the future. We don't think that that can happen during these little years that we each live on this planet. But the reality is that it does.
There are few places left on Earth unexplored. But at the bottom of the world, explorers have found one.
It's cold.
An unclimbed route to one of the Earth's highest places.
This is the joy of being up here on a new route.
There's no margin for error. One slip and that's it. You're gonna die and you're gonna pull off everyone with you.
Antarctica is the highest, driest, coldest continent on Earth.
You get out there and we'll be miserable at times and we'll wonder what the hell are we doing here? And we know what we're doing here. We came looking for this sort of thing.
John Krakauer, who chronicled the worst climbing disaster ever on Everest, with Conrad Anker, a world-class mountaineer, will pioneer a new route to the summit of the highest mountain in Antarctica. Only climbers with strong technical skill and the ability to survive the cold would dare attempt this climb.
You're on, Belay! It's 34 feet low without wind chill.
I've seen a lot of cold weather, but this definitely redefines it. This is kind of what I'd imagined Antarctica would be like.
They're modern explorers with precision equipment and instruments. Yet little has changed since Antarctica's earliest explorers raced to be the first to the South Pole. The risks remain the same.
I just see this beautiful, relatively safe route. Why would we give that up to go out into what to me looks like a really dangerous place?
They'll learn why Antarctica, harsh and inaccessible, is still the last place on Earth. Mountain of Ice, up next on Nova.
This place, to an amazing extent, is truly untrod. I mean, we're going to a place where no one's been before. There's real value in seeing a corner of the world that throws ordinary existence on its head. I mean, I really believe that. One of the greatest joys is being in a place that's so, this unearthly beauty, this, it's a very weird place and a breathtakingly beautiful place. You know, we'll never get to the moon, we'll never get to Mars. This is sort of as close as any of us are going to come, but it's pretty close, really. I mean, it's pretty far removed from day-to-day life in Colorado or Boston or all the places we come from. Antarctica is such a special place and it's so hard to get to. The logistics are mind-boggling.
This is John Krakauer's second trip to Antarctica. Author and adventurer, he's here to climb 45 miles up unexplored glaciers to the summit of Vinson Massif, the highest point on the continent.
When someone offers you a chance to join not only a trip to Antarctica, but an especially interesting trip to Antarctica, it was something I would hate myself for not doing. And we still might not get up this mountain. Last year there were groups that never got out of Punta Arenas, Chile, and that's the gamble you take. We went to Punta Arenas because it's the launching pad for going to Antarctica. It's sort of a hard-edged, working man's town. It's not in a particularly pretty place.
Mountaineer Conrad Anker will lead the expedition up Vinson.
One of the goals of the expeditions is to take a GPS survey to see what the actual height of Vinson is. It was first measured in 1959, photogrammetrically, and then again in 1979. Now, GPS will give us a really accurate measurement of how high Vinson is.
Okay, give the other black one a bit of a push. There we go.
They also want to measure how much snow accumulates there,
Right, in there, Conrad?
which will help determine whether Antarctica is shrinking or growing.
In Antarctica, most of the accumulation studies have been done at the lower elevations. No one has studied accumulation up in the mountains, high in the mountains in Antarctica before.
I'm going to bring my T-blocks, I'm going to bring my pulley.
Okay. This is the snow slide you brought. Boy, that's light.
It's light and it's really sharp.
This is a 100-foot rope.
Weighs
And
about
then-
3 pounds?
Yeah, this is another 100-foot rope. The lighter we can go, the better off we are.
To prepare for their climb, the team has studied the accounts of Antarctica's early explorers. Correctly estimating rations can mean the difference between success and failure.
Our concern is getting the rations enough so we have enough calories to stay warm and do the work we have to do, but not a calorie more because we have to carry this stuff. This has been a problem for Antarctic explorers from the get-go.
It was only 90 years ago when the last great journey of exploration was yet to be made. Two men were leading separate expeditions in a race to claim the South Pole. Roald Amundsen, a Norwegian polar explorer, was taking an unknown route through the transantarctic mountains to reach the pole. Robert Falcon Scott, a British Navy captain, was leading his team up the previously traveled Beardmore Glacier toward the coveted 90 degrees south. Stretching over 2,000 miles across the continent, the transantarctics rise from sea level up to 12,000 feet. 800 miles to the northwest, the Ellsworth Range rises to 16,000 feet. The east side of Vinson is the modern equivalent of the undiscovered South Pole, just waiting to be explored.
The mountain is climbed a lot because it is the highest in the continent. It was first climbed in 1966, and since then, 500 or more people have climbed it. We are climbing it from the exact opposite side that everyone else has climbed it. No one has been where we're going. That has tremendous appeal. We're exploring new ground.
There's only one way for these climbers to get to the continent: flying a C-130 Hercules to Patriot Hills, 600 miles from the South Pole.
There are certain similarities between what we're doing and what those who went before us did. We talk about the ancient explorers, and Scott was there just less than 100 years ago. So this is a continent that doesn't have a long history.
By delving into Scott and Amundsen's journals, John Krakauer will learn firsthand why one explorer returned from the South Pole alive, and the other died trying.
Scott was a very ambitious man, one gets a sense, who wanted to get to the pole because it would make him a hero and make him famous and secure his place in upper crust British society, but you never have a sense that he likes anything about the Arctic or Antarctic.
Scott was a talented writer, capturing the romance of the age of exploration in his journals. Amundsen was a man of action.
Amundsen truly loved the Arctic and the Antarctic. He was a Norwegian who loved being out in the wilderness, and he trained hard. He was interested in adventure and exploration for their own sakes.
Mirrors are in place. Roger, we have mirrors in place.
The runway at Patriot Hills is exposed blue ice, scoured by winds blowing from the South Pole.
Currently wind light and variable. Over.
People on the ground use mirrors as flares to guide the plane down. When the C-130 touches down on the ice, it's too dangerous to apply the brakes.
Antarctica has this mythic weight. It resides in the collective unconscious of so many people. It's like going to the moon, and you can't go to the moon unless you go through Cape Canaveral and NASA or some Russian program, but you can go to Antarctica, and the portal is Patriot Hills. It's the last great wilderness on Earth. So you have this entryway to this pretty amazing little universe of ice and wind and rock and not a lot else. You get this remarkable mix of characters coming through here.
My name is Liz Prescott. I'm here to fly into the pole.
It's about minus 11.5 degrees Celsius. This is an average temperature for this time of the year.
We are two mountaineers. French?
I am Atsushi Yamada. In Japanese style, Yamada Atsushi.
It is a temporary camp with a few pieces of heavy machinery, a radio,
It's very doubtful whether we'll have suitable flying conditions.
and 3 planes to take clients to their dream destinations.
We come from all parts of the world and we're on a quest for the South Pole.
This is how we clean ourselves in Antarctica.
In this tent for 600 miles around, this is the only humanity we have, and it's Christmas Day. I'd like to make a toast. It's for all of us wanting to fly. The weather will be what it will be. The more we're calm, the more we're relaxed about it, the sooner we'll fly.
The more the more you drink, the sooner you'll fly.
Merry Christmas!
When Scott first went to Antarctica in 1902, he sailed on the ship Discovery. Soon after they got there, they experienced their first Antarctic blizzard. But one of Scott's men described this blizzard as, quote, a wind carrying snow dust. For the past several days, we've had strong winds blowing off the polar plateau as much as 70 miles an hour. The snow is very fine, it's sort of sugar-like, it's dense. It is like dust and creates a little swirl and a little vortex. The wind deposits some snow and leaves it there in these dunes that are unlike regular sand dunes. The snow crystals freeze to each other, so these dunes over a period of a day or even hours become rock hard. You punch your shovel into it and it comes out in blocks. The snow isn't falling from clouds, it's been blown there from somewhere else. Been blown halfway across the continent, it has its delicate crystalline edges knocked off and becomes these little microscopic pellets.
Antarctic snow is a combination of actual precipitation and crystals that are blown across the continent. Glaciologist Dan Stone demonstrates how the deposited snow, a total of 1 foot a year at Patriot Hills, will slowly change, becoming harder and eventually turn into ice.
This is the old snow that has been sitting here for quite a while. The snow is going to grow tighter and become more strongly bonded. So this snow will just keep getting harder and harder the deeper we dig.
The accumulated snow is 3,000 feet deep at Patriot Hills and has built up over millions of years into a thick ice sheet.
To understand an ice sheet, it's best to start back at the smaller scale and think about glaciers. We're familiar with them forming in the mountains because there's extra precipitation there versus the lower areas.
Glaciers look like rivers of ice. They take excess snow that has fallen at high elevation and move that mass down to lower areas. As snow accumulates over time, glaciers and ice sheets flow downhill under the pressure of their own weight.
The ice is flowing in part because ice is one of those rare substances that exists very near its melting point.
Here at Patriot Hills, where it's flat, the ice flows 8 meters a year on its long journey to the coast, where it calves off the continent's edges. This can have an impact on global sea level, so scientists watch it carefully to assess whether the ice mass is in a state of equilibrium. They measure how much is gained on the surface each year and how much is lost to the ocean. Since Antarctica contains 90% of the glacial ice on the planet, even a small change in the balance could affect sea level all over the Earth. But under these conditions, making ice measurements is always a challenge. In Antarctica's highest mountains, Conrad Anker and his team will measure, for the first time, how much ice is gained there each year.
Through here to the summit. Our idea would be to land somewhere in here.
The field team meets with 2 twin otter pilots who will drop them off at the base of the Ellsworth Mountains. No plane has ever landed on the east side of the range. The ice is unpredictable. The maps, inaccurate.
These mountains haven't been that carefully mapped. This map was drawn from a series of flights in 1959 by U.S. Navy aircraft. We have some of the photos they took, but because no one's been on the ground here, there's been no field checking of the data. These pilots were taking it very seriously. Wow, we don't know what this is like. We don't know if we can even land. They were hedging their bets.
You just want to be able to see well to make a smooth landing and to be safe.
I'd say that'd be the best bet, right on top of that.
On top of that?
Fully loaded with 1,200 pounds of food, fuel, and equipment, they'll fly 220 miles over the frozen continent. They'll be dropped off in a place where no one has been before, left alone amidst a sea of ice to survive on their own for the next 17 days.
The lines of support are so few, the lines of communication are so few. You are really on your own here in a very real sense. There are 3 tiny airplanes here, the only aircraft in a whole half a continent. These pilots were very worried about crevasses, which occur anytime the glacier isn't flat. They were worried about sastrugi, snow formed by the wind into these thorns and little ridges and ripples that can be rock hard and break planes' skis.
Clouds begin to gather as the Twin Otter approaches landing, obscuring the pilot's horizon. There's little distinction between ice and sky.
We're right now at 3,800 feet, and the summit of Vincent is 12,300 feet higher than us right now. So that is a lot of, that's comparable to the vertical rise of any mountain on Earth. Everest rises 12,000 feet.
The climbers are about to set out on a vertical journey across the ice. From here, they'll attempt one of the greatest elevation gains possible on Earth. The base to summit vertical rise from this side of the range is much greater than the other side, where Vincent is traditionally climbed. Antarctica's mountains act as a dam, holding back the ice of the polar plateau with an average elevation of 10,000 feet. This is why it's the highest continent on Earth. Without its ice, Antarctica would average only 1,500 feet above sea level. 100 million years ago, global climate was warm, and there was no land ice on Earth. 50 million years later, the Earth began to cool, and the first ice in Antarctica appeared here, in the Ellsworth Mountains. Today, glaciologists watch the fluctuations in the amount of ice covering the Earth. Because Antarctica holds most of the world's fresh water, assessment of its total mass helps scientists predict the future of sea level rise and also climate change. The ice here reflects solar energy back into space, which helps keep the planet cool. If Antarctica's ice were to shrink, there could be an acceleration in the global warming process. A subtle shift in the total amount of ice here would be a warning for climatologists.
We want to know whether a glacier or an ice sheet is growing or shrinking. And to understand that, we have to understand what's going into the glacier, how much ice is accumulating on an annual basis, and then how much is being lost. And so this looks like pretty good right here.
To learn how much snow is gained here each year, they have to dig into the past and excavate a 2-meter deep snow pit.
So, we've dug one pit.
Let's dig another.
Here's number 2.
A tarp is laid over the first pit, and light shows through the adjoining wall.
Nice in here. Looks like we've got at least a few layers that look like annual layers in here. So we've got the alternating dark and light bands. Light, dark, light, dark. So the light's the lower density snow, and this is the denser stuff. So this would probably be the stuff that fell over the winter. So we're going to take some density measurements here. We get a sample that's exactly filling this box, and that's 100 cubic centimeters. And we'll put that in a little bag and weigh it.
Okay.
So that'll be our sample weight, recorded in grams. We're going to do that for each one of these representative layers.
Okay.
32 grams. Yeah, that's definitely denser than the other stuff. So this is more the finer, probably a winter snow, the wind-blown stuff. And the summer snow is basically bigger crystals and lower density crystals, letting more light through.
Like rings in a tree, Dan can see 8 years' worth of snow layers represented in the pit wall. The result? 9 inches of snow accumulates here each year. an equivalent of less than 2 inches of annual rainfall. This is normal for an arid environment. Despite the tremendous volume of water stored here as ice, Antarctica is one of the world's great deserts, a storehouse of information about past climate.
Now that Dan and I have worked on a snow pit together, and we can see the stratigraphy that the snow lays down annually. And each pit we dig is going to tell us more about the snow, how it changes seasonally.
Andrew McLean has to figure out how to hold instruments and camera equipment up Vinson.
Andrew, what are you doing?
Attaching mascots to the sleds to help kind of guide us and act as guardian angels to these massive beasts that we're rigging up here. This is the biggest sled, so it's got the little dude on it. And we have a Minnie Mouse, and then we've got the little flying troll as well.
In the polar tradition, all food and equipment, including a solar panel to charge the camera, will be hauled 45 miles to the top of the continent. Like Amundsen himself, this expedition is on skis.
Amundsen, as a young man, he decided polar exploration was what he wanted to do. And he realized early on that he needed training, so he sought out people who could teach him skiing. He did a very ambitious ski traverse across a high plateau in Norway that had never been done before. When he finally goes to the South Pole, it's clear from his journals that he doesn't think this is that much different from what he did in Norway as a young man. It was just longer and a little colder. Scott was a product of the times. He was a career Royal Navy officer. He had a sense that gentlemen didn't try too hard. For instance, he had never tried skiing or dog mushing until the first time he was in Antarctica. They got there and then figured out how to ski. Didn't research what the best bindings were, which boots you should use. And he concluded, because he didn't know how to use these things, that they were pretty much worthless. So for much of Scott's Antarctic travels, his skis would be on his sledge and his men would be post-holing with these awful loads. In his journal entry for January 4th, 1911, Scott writes, "After many frowns, fortune has treated us to the kindest smile. For 24 hours we have had a calm with brilliant sunshine. Such weather in such a place comes nearer to satisfying my ideal of perfection than any condition that I've ever experienced. The warm glow of the sun with the keen, invigorating cold of the air forms a combination which is inexpressibly health-giving and satisfying to me, whilst the golden light on this wonderful scene of mountain and ice satisfies every claim of scenic magnificence."
After 7 hours of heavy hauling, the team has advanced 9 miles. Between his sled and backpack, Krakauer has moved over 150 pounds of gear up to their second camp. From here, the terrain will become much steeper. They'll have to find a route that avoids the large glaciers tumbling down around them. When the gradient is steep, glaciers break up and become ice falls, carrying large teetering blocks called seracs, the size of houses. To Dan Stone, ice falls are a classic sign of ice flow.
Broken up ice means things are flowing. Just like a waterfall in a river, the ice is extending as it comes to the ice fall. It's stretching in the down glacier motion to the point that it breaks, forming all these seracs.
Huge cracks or crevasses open up as the ice flows downhill. Some are visible, but most lay hidden underneath the smooth surface of accumulated snow. It is now the third day of the climb. Dan digs another snow pit, as the others are busy carrying loads up the glacier. The food and equipment weighs more than they had hoped.
We didn't think we would have to double carry every day. From day one, everything's taken twice as long. We've had to go to the next camp, dump a load, go back to the first camp, and the next day move camp. So we're moving half as fast. We still only have the same amount of food and fuel, 17 days. We have been hammering hard every single day, exhausting ourselves.
The team is led out of camp by Dave Hahn, an Antarctic field guide who specializes in glacier travel. He's climbed Vinson more than any other person, 19 times, but from the traditional route on the other side of the Ellsworths. His pack weighing over 100 pounds, Dave's ski pole breaks through a hidden crevasse.
Yeah, we're right on top of it. You're on it too. Let me get back off to this. Well, we got a rope, Conrad. This is fine. This will be fine. All right, well, I just plunged my pole through it, so...
Dave, at one point, put his foot down and said, I'm really uncomfortable with the way this is going. This is not smart. Someone's going to fall in a crevasse, and we're going to all feel stupid.
While the others continue over the snow-covered crevasse, Dave stands alone in disapproval.
Well, I'll see what you think. If someone wants a rope, let's do it.
Guys, we need to do it before it, not while we're on it. Exactly. This way we're going to find it when it kills one of us.
Dave just put a ski pole in a crevasse 100 yards down. Would have been a bad scene if any of us had gone in. So we're going to play it a little smarter and rope.
If you fall in a crevasse with a rope on, there's still a good chance of getting hurt. But if you fall in without a rope, not too many people have lived to tell about it.
This quote is by Amundsen, his first impression of Antarctica. The country here is just one single glacier. To go alone in it is pure madness. Two roped together, absolutely necessary.
Conrad, the
green
chef.
The great green, greasy glop.
Well, the theory here is that it all gets mixed up anyway.
So what's in this, Conrad? I saw you throwing stuff madly, but I didn't really catch it.
We've got hummus, falafel, 2 tasty bites, some syrup, cheese, mozzarella cheese, real maple syrup, garlic powder.
Any other bowls out there?
Ready? Samples.
Oh, tofu.
That makes me sweat.
I like the way the cheese sticks to my beard fuzz.
Oh, there's beard fuzz added to this?
Dan digs his third snow pit as John Krakauer looks on.
It's fun watching him work because he's meticulous, he knows his methodology.
31.
I've learned quite a bit just from watching him and asking him simple questions about why snow does the weird things that it does.
In this pit, Dan catches snow in the process of turning to ice.
Is that the densest we've seen?
Yep.
It's pretty dense stuff. It's real strong. I mean, this it's like an ice cube. There, I can squeeze it and break it apart. And I picked off what I think may be the boundary between a summer-winter transition on an annual basis, and I've got 1, 2, 3, and then down into the 4th year.
At this elevation, 8,000 feet, the annual snowfall is double that of the first snow pit. Here, 18 inches accumulate each year. It's not surprising to the climbers, who find the weather takes a turn for the worst as they move higher.
You guys ready?
It's snowing right now, lightly. Everyone talks about Antarctica as this desert with less precipitation than the Sahara. These snow crystals contain very little moisture, though. They hit my glove and they evaporate almost instantly because it sublimates. It never really forms pools of water. It just evaporates away. It goes directly from snow to vapor.
The vapor contributes to cloud formation, a great hazard for the climbers.
It's been described several different ways. 0-0, inside of the ping pong ball, inside the milk bottle. But what we have here is a situation where there is no horizon, there is no contrast. Looking forward, the only horizon we can see is where the pass comes down. But between here and there, it's completely white. It can be really disorienting as you move along. The conditions are unknown. There could be a crevasse.
Like Amundsen, these climbers have honed their skills on other glaciers before coming to Antarctica.
Amundsen took the trouble to go and study with the Eskimos and learn how to drive dogs. The whole process for him was glorious. The dogs are hauling the loads on the sledges, the men are skiing beside them. One of their skiers was a champion ski racer. The British, on the other hand, Scott's team, barely knew how to strap these things on their feet. Scott, because he didn't appreciate the value of dogs, they tried hauling with motorized sledges, snowcats as it were. And then they had ponies, which are terribly poorly suited for the snow. And after the last of their ponies died, or they shot the pony for food, they had to start man-hauling. Unlike Amundsen, who was appalled by this stupid, toilsome work, Scott says, well, at least we can begin the man-hauling. This is the way it should be. He had this Calvinistic streak. This business is supposed to be painful and hard and purifying and just very different than Amundsen, who was out there enjoying himself. For Scott, it was supposed to be an ordeal, and by God, it was.
The team has been manholing for a week, and what lies before them is even more grueling than the terrain they've covered. At the top of a high pass, they get their first glimpse at the most difficult part of their route, a 3,000-foot head wall.
So Conrad,
Yeah.
what do you think looking at this head wall?
My first priority would be to look at a line that's free of objective hazard.
The head wall, it's really complicated. It's huge. It's this wide expanse of jumbled ice, this chaotic assemblage of teetering seracs.
We don't know what triggers serac activity. Why do we want to know about them as climbers? Because you don't want to get in their way. We have no idea when they release. They release according to temperature. They can release by a geologic jiggle that will then send them down. They are one of the greatest hazards we're going to encounter on our route.
There's no margin for error. One slip and that's it. I mean, you're going to die and you're going to pull off everyone with you on the rope. If you're roped up, and you have to be as fast as... If it was up to me, I wouldn't encumber myself with making a film at all. Climbing the peak is plenty of challenge. Maybe we can do it, but maybe it's time to really have a reality check here.
No.
We have 2 people on this expedition, the producer and the cameraman, who are relatively inexperienced, and the most difficult and critical judgments that have to be made concern the safety of the team on the head wall.
There's no way I'd be going on any of that without a rope.
I'd be nervous guiding that.
You could definitely weave through the middle, but then you're going to be exposed to almost every serac on the face there.
They climb down to set up camp below the base of the head wall. They'll regroup and decide how to handle the challenge.
We're all itching to get up there. Today we got up at 6, and right away it didn't look promising. You could see these mare's tails of spindrift just ripping off the plateau towards us, blowing like hell up there, hurricane-force winds, depositing great amounts of snow. The wind descended, we saw it above us, and then these gusts of wind came down the mountain, and Dave said, "Look out for any loose sleeping bags, tie down the sleds." We scrambled around, packing stuff and tying stuff. And the wind hit, and it was bitter cold. It was 5 below 0, and the wind chill was pretty intense.
Even though the windstorm dies as quickly as it arrived, Dave warns them that the weather could get worse.
All through this trip, there's this dynamic where I've been saying, yeah, looks great, and Dave is always the voice of caution, sort of gloom and doom. Not so fast. You gotta worry about the weather, you gotta worry about this route. He's always the naysayer, and your mother telling you to wear your raincoat. That's Dave.
If the weather stays lousy, not gonna be able to do everything. I mean, something's gotta give.
Almost every time he goes climbing, he's guiding. He knows how to get inexperienced people up and down mountains safely.
They climb up to a point where they can take a closer look at the head wall.
I didn't want to go in those seracs. For much of the climb, you would be beneath these huge ice blocks towering over you, waiting to tumble.
They've narrowed it down to 2 possible routes. Both have their risks. One is proposed by Krakauer, and the other by Dave Hahn.
The route Dave found was circuitous, and it wove around and beneath seracs and crevasses, and I flat out said, I veto that. I'm not going there. To the left of that is this beautiful rock rib. Well, there was no chance of being hit by falling ice. It was steeper and more technically difficult, which actually was part of the appeal. But that's what I wanted to climb. Dave correctly pointed out that it wasn't realistic to get some inexperienced team members and all this ton of gear up. So we had this fairly heated debate. I just see this beautiful, relatively safe route from what is the part of it we can see. Certainly much safer than this. And why would we give that up to go out into what to me looks like a really dangerous place?
The way we would normally do it is we would compromise the safety a little bit from serac fall to lessen the danger of a fall from steepness.
If that was the only route up this, I could maybe justify it. But there's this beautiful, relatively safe route right next to it. And what we gain by going over there, which is maybe getting 2 inexperienced film crew up there, is not an acceptable risk to me.
What do you think, Conrad?
Well, It's a tough one to have to make a decision. Every hour you want to make a different decision.
I'd be willing to keep going. If it means we could do science tomorrow, and you guys could just come up tomorrow.
Well, Dave, if they go up, what do you think we ought to do? I don't know.
We got to a place where the two routes diverged. It was either time to go up the rock rib or head right into the Seracs. And it was late. Dan and I ended up pitching our little tent, this beautiful place we called the Hourglass Bivouac. And when everyone else went down, we continued up.
The team splits up. Anchor and Hahn climb down to carry up more loads. And Krakauer and Dan Stone take the steep route, unroped, to avoid accidentally pulling each other down the head wall.
It was real climbing. And if you slip, there was no rope, you're going to go a long ways, go 3,000 feet.
Krakauer documents their climb on a mini DV camera.
Well, we got a ways to go.
Really?
Yeah. Halfway, maybe.
When the team left Dan and I up there, we all agreed there's no debate, it's settled. We're not taking the film crew up this mountain. There's no way they can climb this.
Dan and I are carrying big loads.
I would much rather trust my own skill and judgment and experience than trust a glacier that may or may not shake loose a 300-ton block of ice on me. So it was an obvious choice.
At 12,200 feet, John and Dan safely reached the top of the head wall. They had to climb it twice to advance their heavy gear to high camp.
So a little after 10 in the evening, we recently arrived here at the high camp on the plateau. It's 10 below, maybe 12 or 15 below. We made 2 carries up the rib. It's great to be here, an amazing place. We're looking forward to the team arriving tomorrow and going on to the summit soon thereafter.
3,000 feet below, near the base of the head wall, the others are stuck in a whiteout.
We're up here at the cache that we've established between the Hourglass camp and the Dater camp, and we had hoped to go up to the Hourglass and hopefully the upper plateau today. Unfortunately, the clear weather that we thought we had early in the morning has gone south or turned into 0-0 conditions. So we're pitched the tent in hopes that pitching the tent's going to make the weather clear, and we're sitting here idling away our time, enjoying a little jerky and some humor. Dave's singing us songs.
Oh, I just don't know where to begin.
9,200 feet. 6 people in a tent? 3-person tent?
In the morning, they learn that the whole team, including the camera crew, is on its way up.
Dan and I called down, and where are you guys? Conrad says, yeah, we decided the whole team's going now. And Dan and I looked at each other and our jaws dropped. And, what is going on? This whole thing is falling apart. Time is running out. And these guys are around trying to, who knows what, get everyone up this thing. But this is going to cost us the whole trip. We're not going to get to the summit. The film's going to be a wreck. What a mistake.
The others begin climbing the head wall. Conrad steps into a crevasse.
A little bit of a hole, Andrew.
And that's when we sort of said, okay, we'll wait 1 day for you guys, but we're not going to wait for 2. And you better get up here, or we're going to go for the summit and enjoy yourselves down there in this cloud.
They've chosen Dave Hahn's route through the Seracs, much to John's disapproval.
I've been on one guided expedition in my life, and it was the biggest mistake I ever made.
Some hollow stuff in there, Andrew. Okay.
I've seen what happens when very good guides make a single poor decision with clients who don't have the skills or the experience to look after themselves. I swore in the past that I would never be in this situation again, and this is just a little too close to that for me.
All 6 of the remaining team, climbers and film crew, led by Conrad Anker and Dave Hahn, arrive safely at high camp.
Oh, this is great. Come into this.
And, you know, Dave was right. It worked. It was a gamble.
Good time, you guys. Good going.
He did a remarkable bit of guiding. He knows this mountain, he knows this range. I came away with a great deal more respect for him after seeing what he did.
They are camped on a high plateau just above the headwall, where the ice cascades off the mountain. Dan and John dig the highest snow pit in their study. Their shovels strike thick layers of hard crust. After hours of effort, they're able to count 4 years' worth of snow layers, for an average accumulation of 15 inches a year. There is less accumulation at high altitude because winds on the upper mountains scour loose snow off the surface. This is the first attempt to measure snow accumulation in the Ellsworths. And the information can also be applied to the Transantarctic range, where even less is known. With data collected from all over the continent, scientists are learning that the Antarctic ice sheet appears to be in a state of equilibrium, neither increasing nor decreasing significantly. They will continue to watch the ice carefully, as its delicate balance can affect worldwide climate and sea level. It is minus 12 degrees. The team prepares to leave high camp to climb the last 4,000 feet of their journey to measure the height of Antarctica's highest mountain.
The real moment of truth is summit day. Things can happen so quickly. You can be fine 1 minute, but if your mitten blows away, you're screwed. You better have a spare mitten fast, or your hand is wood. And if your hand is wood, you can't zip up your jacket, you can't tie a knot, you can't do anything.
Come on, mitten somewhere.
It's sort of like going into outer space. You got to have your spacesuit on and make sure there's no leaks.
Life is complicated in the cold.
The cold and the thin air are insidious. They don't remind you that they're out to hammer you at any moment. You're just this little fly up there, and the cold and the altitude are this big swatter, and they're just waiting to whap you. Scott, as he approached the pole, he and his men were growing hungrier and hungrier. They were starting to suffer the effects of scurvy. They were literally wasting away from starvation to the horrible cold. Scott wrote, "We notice the cold. It is a critical time, but we ought to pull through. Oh, for a few fine days. So close it seems."
On the same polar plateau, Amundsen wrote, minus 28 degrees. A little cool to go against with our sore faces, but nothing to make a song about. Sledges and ski glide easily and pleasantly.
The accrued fatigue, it all caught up to me. Maybe it was the altitude, I don't know what. I was just maxed out. Vincent was just this big hulking blob in the distance, and we weren't even sure what the summit was. People confuse it. They're always calling it Mount Vincent or Vincent Peak, and it's Vincent Massif, and it's a really appropriate name because it is this massif. It is this hulk of rock and ice that defies easy description. It's so big that it hides itself. It's so big that the summit remains hidden until the penultimate moment.
It is really, really cold. Whew. Okay, let me catch my breath. Are you rolling?
Yeah.
Okay, we're here at the summit plateau just below the top of Vincent. It's over here behind me. It's the leftmost little knob on that ridge. We're gonna go up to the pass and then climb the ridge.
After you've labored up the back of this big elephant, the summit is this nice little mountain on top of the big mountain, sort of junior Vincent, this beautiful slender ridge that curves up and falls away steeply on both sides. That final quarter mile, you're sort of dancing along this knife edge of ice and rock.
Come to Vincent! It'd be better if it was warmer!
From a climber's point of view, it was a very pleasing summit.
Good job, Dave, man. Awesome job of guiding. You are the best guide I have ever seen. I'm serious.
Let's see if we pull the day off.
Yeah, I shouldn't count my chickens, but good job, man.
Thanks.
Awesome
man.
job.
Appreciate
awesome. That. It's 34 below without wind chill.
34 below?
Yep.
Wow! What a place!
The wind chill is minus 70 degrees. They need to descend quickly.
You can just go like hell.
Okay.
People are getting cold. Our cameraman got a frostbitten finger. I certainly have learned from really bitter experience that the climb isn't over till you're back down in the tent at the base of the mountain.
Dan has only a few minutes to measure the height of Vinson. He balances a precision GPS unit on the highest piece of rock.
I'm trying to take a GPS reading right here. Having a real hard time because it's so cold. It's like I've got about 9 satellites.
After running the GPS for 20 minutes on the summit, Dan obtained the first high-precision ground-based measurement of the highest point in Antarctica. The data confirms that Vinson is 16,077 feet, as much as 10 feet higher than previously thought.
On January 17th, 1912, Scott arrived at the pole, 34 days after Amundsen had already been there. And when he got there, he found a tent that Amundsen had left, and it was just utterly demoralizing for Scott and his 4 companions. Scott wrote in his journal, "We've had a horrible day. Add to our disappointment a headwind 4 to 5 with a temperature of minus 22 degrees and companions laboring on with cold feet and hands. Great God, this is an awful place and terrible enough for us to have labored to it without the reward or priority."
But when the Norwegians finally returned to their ship, Amundsen reportedly said, "We haven't got much to tell in the way of privation or great struggle. The whole thing went like a dream."
There's a very famous quote that I always think of. I actually used it as an epigraph in my first book. It's by the great polar explorer Stefansson. "Adventure is a sign of incompetence." If you have an adventure, you're doing something wrong. But if you really plan things out in the vein of Amundsen, you don't have adventures. Everything goes smoothly like a dream. On March 29th, on their way back from the pole, Scott and his men haven't eaten for a week. Scott wrote, "Outside the door of the tent, it remains a scene of whirling drift. I do not think we can hope for any better things now. We shall stick it out to the end, but we are getting weaker, of course, and the end cannot be far. It seems a pity, but I do not think I can write more."
Scott had already lost 2 of his men to exhaustion. He and his 2 surviving companions slowly starved to death in their tent, 11 miles from their next food cache.
I think what we're doing here is sort of a perverse thing. We're deliberately hoping we have some adventures, but not too much adventure. And we'll wonder, what the hell are we doing here? And we know what we're doing here. We came looking for this sort of thing. People have always gone to the poles for a sense of adventure. They've justified them by saying, oh, we're looking for a Northwest Passage, for commerce or for science. But I firmly believe that the real motivation was people doing what we're doing. And they wanted to go out and get scared and get miserable and enjoy themselves in a way that you can't really understand unless you do this stuff and like to do this stuff.
Home sweet home.
That feels good. I'm whipped. Going on adrenaline for the past 5 or 6 days. Now the adrenaline's all gone. And it's like no more gas in the tank. And the pack is so heavy. So, yeah, I don't have a lot left. I'm kind of running on vapors.
They call for the twin otter, and luckily, a day later, conditions are perfect for a twin otter to make a first-ever landing on a glacier on the east side of Vinson.
To be in an unexplored country, it's a rare thing, getting rare all the time. Yeah, we pioneered a new route up Vinson, but more than that, it was just being in an unknown place for 17 days. It seemed too much to believe that we could actually have the whole side of the highest mountain on the continent to ourselves, and that we could have been the first people there. That doesn't make sense. Why didn't someone go there before us?